So, as I mentioned, the atmosphere distorts our view of space and things above the Earth. And two different ways that we have figured out to get around that problem are called adaptive optics and the use of space telescopes. So, first, I'm going to talk about adaptive optics and a little bit about the problem of atmospheric distortion as well. The horizontal lines up at the top of this image are supposed to represent light waves coming into the atmosphere from space. Because the atmosphere is turbulent, the air is moving, different pockets of air have different temperatures and different densities. As those light waves travel through that turbulent air, their direction of travel is going to be bent. Light travels faster or slower depending on the temperature and density of the air it's traveling through. And so parts of the light wave are going to be bent differently from other parts. And the light waves that come out of that turbulent air are going to be distorted and bent, as shown by the perturbed wave fronts at the bottom of this image. So that's the problem of atmospheric distortion. And it is sometimes described by astronomers as the seeing of a certain location. Seeing, S-E-E-I-N-G. And if the seeing is good, that means the disturbances are very minor, and if the seeing is bad, then they're more major. Here's a little bit more about seeing. This could be the image of a star taken with a small telescope. And it's kind of blurry and kind of difficult to understand, and so we might think, hey, if we just had a bigger telescope, we could magnify this more, or we could get a clearer view of it, we could collect more light, and we'd be able to see actually maybe the surface of that star, right? Maybe we'd be able to see more detail. But because of seeing, because of the distortion caused by the Earth's atmosphere, that turns out not to be possible. Here's what it would look like if we magnified it more. Actually, not if we magnified it more, but if we used a bigger telescope and got a clearer picture of this thing, the same amount of light is going to still be just spread out and smeared out. And the star itself does not look like this, but the distortion caused by the atmosphere, the seeing, is what's causing this spreading out, this smearing. Okay, and so getting a bigger telescope, you're not going to be able to see the star any better, and the atmosphere is going to end up limiting how good of a view you can get. So we have to figure out a way to beat that. For some really dramatic movies of what seeing does to astronomical observations, please pause this movie for a moment and go check out this website. There's some really awesome videos that this person has put up there. They've looked at the moon and some other things out in space with a small telescope from the ground, and you can just see the sort of boiling effects of the atmosphere. It almost looks like when you look above the hood of a hot car or a hot street or sidewalk on a hot day, and you can see the air and the images behind it swirling and changing. And it looks just like that. So please have a look at this website and you'll see what I mean. This is all about seeing and atmospheric distortion. And then we'll talk about the two strategies for getting around this atmospheric distortion. The first one is called adaptive optics. Adaptive optics uses the idea that even though the light coming through the atmosphere is distorted by differences in temperature and density in the air, if we can figure out what those distortions are exactly, we can bend our mirror to correct for them. And that's what this diagram here is trying to show. If an image from an object coming in from the sky is deformed because of irregularities in the air, if we then deform our mirror in a corresponding way, the resulting image could be nice and uniform. And usually this works by using a laser and shooting a laser up into the sky and observing that through the atmosphere and seeing how that perfect laser image is distorted, and using the information from that several hundred times per second to adjust the mirror. The mirrors that do this have what are called actuators behind them. This is showing you a picture of the actuators on which a giant mirror is going to be placed. Each of those little cells that you see there can be pushed up and down very quickly with very high precision, several hundred times per second, in response to the measurements that are made of distortions caused by irregularities in our atmosphere. And if you push and pull on each part of the mirror, you can bend it and twist it in ways that will correct for all of the irregularities and distortions caused by the atmosphere. So here's an image of that adaptive optics mirror fully assembled. Now the mirror is resting on top of those actuators. And it doesn't move much. I mean, you can hardly see it, but it moves very quickly and in a very precise way, and it is enough to correct for the smudgy smearing effect that the atmosphere has. Now I want to show you a picture that results from this kind of technique. This is an image of a faraway galaxy of stars, called a starburst galaxy. The image on the left is the image obtained with the adaptive optics technique, and the image on the right is the image that you would see without such a technique. You can see the difference. The detail in the right side image is all smeared out, and you can't really see what it is. By compensating for the distortions in the atmosphere using adaptive optics, by basically bending and twisting the mirror, we can clear up a lot of the problems that astronomers have with atmospheric distortion. This is a great technique. It's very expensive and very difficult, but it is doable. But it can only take you so far, and even the best adaptive optics systems today are no match for a better solution to the problem of atmospheric distortion. And so let's take a look at that next. Now, if you want to get away from all the atmospheric distortion that hampers a lot of observations from Earth, well, you build a telescope in space. This is the Hubble Space Telescope. Not the first, but certainly one of the best space telescopes we've built. It was launched almost exactly 19 years ago. It has a mass of over 11,000 kilograms. It orbits the Earth, well, about once every an hour and a half, so it's moving quite fast. The diameter of that little open door tube there is almost 2.5 meters. So the primary reflector, this is a reflecting telescope. The primary reflector is something like 2 or 2.5 meters in diameter. The focal length of that reflector is nearly 60 meters, so if it wasn't a reflector, this thing would have to be much longer than it is. And the Hubble has given us spectacular images from all the different things in space. Starting with something relatively familiar, here's a picture, a close-up of Jupiter, the biggest planet in our solar system. And this picture was taken from the Hubble, which is very close to Earth. Which is amazing that from so far away we get such a detailed view of Jupiter's clouds and storms. And in this picture you can see the big red spot, the largest of the red spots there, is a new red storm that's forming on Jupiter. And this picture was the first evidence of that. But Hubble can see a lot further than just Jupiter. Here's a picture of some stars in our galaxy. Each of these points of light is a star like our sun. And even the closest of them is hundreds of light years away from us. Much further than Jupiter. So far that even with the Hubble, these things still just look like points of light. We can't see the surface of these stars at all. But it is beautiful, and these pictures from the Hubble of these star clusters are fantastic pictures. It's thought that our sun formed in a cluster of stars, something like this, 4 or 5 billion years ago. So all of these stars are in our galaxy, our island in the universe. But there are many other islands out there, and Hubble can see those galaxies also with astonishing clarity. Here's a beautiful example. It's a galaxy similar to our own. It's a spiral galaxy. You can see lots of stars and lots of dust. And you can see there's something very interesting going on in the center. We'll have to talk about that soon. Each galaxy contains something like 100 billion stars, and, well, as far as we have seen, we've seen at least 100 billion galaxies, each with 100 billion stars. Here's a picture of a tiny piece of the sky. That red thing with the cross coming out of it toward the bottom of the picture is a star in our galaxy. But everything else that you see in this picture is a galaxy of stars, each containing hundreds of billions of stars in its own. And wherever Hubble looks, in whatever part of the sky it looks, it sees this kind of richness. There are that many galaxies out there in every direction. This is from a famous image that the Hubble took called the Hubble Deep Field, where it just tried to look at the darkest patch of sky it could find. And even there, it saw all these galaxies out there. So Hubble has really opened our eyes as to the richness and the beauty of the universe.